Welcome to this Trian channel. This video is part of a series of videos discussing an introduction to mathematics for economics and business. And in this video, the topic is optimization. Optimization is perhaps one of the most important applications of the concept of derivative in economics. And the optimization that we will discuss in this video will be applied in profit maximization, one of the most important application of optimization in economics. This is the part 1. In this part 1, we will mainly discuss the concept of optimization in profit maximization. And in the part 2 of the video, we will discuss the application in an example. Before discussing optimization, let's first review our understanding about derivative. When we have y, a function of x, the derivative of y with respect to x is the first order derivative. And then when we take the derivative of this derivative with respect to x, it means we are taking the second order derivative. So it is the derivative of dy over dx with respect to x. So we have d squared y divided by dx squared. And then we can continue with the third order derivative. So it is the derivative of the second order derivative with respect to x. So we have here d cubed y divided by dx cubed. This is the third order derivative. And then this is the nth order derivative. And then this slide shows a graphical illustration. We have three y, a function of x here. This is the first, the second, the third, and the fourth. So we have four functions here. We have four graphs here. And then from this graph, we're going to take the first derivative and then the second derivative. Remember that derivative is basically the slope. It shows the slope of a graph. When we have this graph here, so the slope here is the derivative. The derivative here is the slope. We can see here that the slope at this maximum point is 0 because the slope here is 0. So the derivative here is 0. It is flat here, so the slope is 0. And then when we see this part of the graph, the slope here is positive, but it is becoming flatter. So it is positive, and then it approaches 0. And then from this point to the right, we can see here that the slope now is becoming negative. So we can see here the derivative is negative here. And it is becoming steeper. So the slope increases, the negative value increases. Okay, this is the first derivative of this graph. And then the second derivative is the slope of this graph. This is the second derivative. So this is the derivative of this derivative. So it means this is the slope of this graph. We can see here that this graph, the steepness of this graph is constant. The steepness does not change. So the slope or the derivative is constant at a certain value. And because the slope here is negative, so the derivative here is at a negative value. Let's see the second function here, the second graph. At the minimum point here, the slope is flat. Yeah, the slope is flat. The slope is 0. Okay, so it is 0 here. and then the slope at this area are negative. So the derivative here is at negative values. At this area we have positive values for the slope, and we can see here the slope here is when we approach the minimum values from left side, we can see here that the slope or the graph is getting flatter, so it approaches 0. Here we have negative values and it approaches 0, and then when we move from this minimum point to the right, the slope increases. So we can see here the derivative increases. And similar to this graph here, the slope of this graph is constant. So the derivative is also a constant value, and because it is positive, so the derivative is positive. Because it is a straight line, the derivative of a straight line is a constant. Okay, and let's see the next curve. We can see here that the curve is concave at this area and it is convex at this area. So we have a point here, an inflection point. This is a point where the curve changes from concave to convex, so it is called the inflection point. And then when we move from left to the right, you can see here that the steepness or the slope decreases to a certain value here at this point, but from this point to the right the slope increases. That is why the derivative here at the beginning decreases, and then reaching a certain minimum value, and then from this point to the right it starts to increase. Okay, and then the derivative of this derivative here, the second derivative, the derivative of this derivative, so it is the slope of this derivative. It is like applying the first derivative to this convex graph. We can see here at the minimum the slope is 0. When we move from the left to the right, the slope decreases here, approaching 0, and then increases. Here the negative values decreases, it approaches 0, and then from this 0 point the slope starts to increase. Okay, and the last one, it is the opposite of this graph. It starts with convex, and then it changes to concave. So the point where the graph changes from convex to concave is somewhere here. It is called the inflection point. And slope, we can see here, at the beginning it is increasing, it becomes steeper and steeper, and then it reaches maximum slope. The steepness is maximum, is somewhere here, and then from this point to the right the slope starts to decrease. So we can see the derivative here. At the beginning it is increasing, reaching a maximum, and then decreases, and then the derivative of this derivative, this is the derivative of this derivative, or the second derivative. At the maximum point here the slope is 0 because it is flat here, 0, and then at the beginning the slope decreases 0, and then from this point to the right it starts to be negative. The slopes are negative, and the negative value increases because it is becoming steeper. So we can see here the slope at the beginning decreases 0 and then negative, and the negative values are increasing. Okay, I hope this can refresh our memory about the graphical illustration of derivative. Now we're going to make some conclusions. When we have a maximum point here, the y, a function of x, is at maximum. The first derivative is 0, and then the second derivative is less than 0. So when the conclusion is when the first derivative is 0 and the second derivative is less than 0, the original function or the total function is at maximum. And when we have a minimum, the first derivative is 0 and the second derivative is greater than 0. So the conclusion is when the first derivative is 0 and then the second derivative is greater than 0, it means we have a minimum point here at the original function. It also means that when the first derivative is 0, we have two possible things of the original function here. It can be a maximum or minimum. We can only know that it is maximum when the second derivative is less than 0, and it is a minimum when the second derivative is greater than 0. And for inflection point, when the inflection point is changed from concave to convex, the first derivative is at the minimum point here, and the second derivative is 0. Okay, so when the second derivative is 0 and then the first derivative is at the minimum point, it means that we have an inflection point, which is a point of change from concave to convex. And the opposite things are happening here. It is a point of change. The inflection point is a point of change from convex to concave. So we have a maximum point for the first derivative, and the second derivative is 0. Okay, these conclusions will be very useful in doing the optimization in the next slides. There are two kinds of extremum, relative and absolute. When we have this graph, the point here is the absolute extremum. This is the absolute maximum because there are no other parts of this graph any higher than this point, and this is the absolute minimum. This is an absolute extremum because no other parts of this graph are any lower than this point. The same thing for this one. This is the absolute minimum of this graph, and this is the absolute maximum. Okay, and this red point is different. This red point is different because it is maximum. This is an extremum, but this is not the absolute extremum, because yes, it is maximum for this area, from this area to this area, to this part of the graph, but it is still lower or less than this point. So we cannot call this as the absolute maximum. It is only the relative maximum. The same thing for this one. This is the relative minimum. This is relative extremum. And for this relative extremum, we can apply the conclusion that we have made from the previous slide, to decide whether it is a maximum or a minimum. The necessary condition from the first derivative test is that it is a relative minimum or a relative maximum if the first derivative is 0. So when the derivative is 0, it can be either relative maximum or relative minimum. That's the necessary condition. To decide whether it is maximum or minimum, we need to apply the next condition, or the sufficient condition. The sufficient condition is in the next slide. The sufficient condition to decide whether it is maximum or minimum is using the second derivative test. From the graphical illustration, we have concluded that when the second derivative is less than 0, so the point that we are talking about the original graph is maximum point. So we can conclude that it is a relative maximum. And when the second derivative is greater than 0, it means that what we have as the point in the original function and the original graph is a minimum point. So it is a relative minimum. The next thing to do is applying the test in optimization. As an example, we're going to use a case of maximizing profit. Profit is basically revenue minus cost, because revenue is a function of quantity and cost is also a function of quantity, so profit is a function of quantity too, because profit is revenue minus cost. And the question in optimization is, what is the quantity or what is the optimal quantity that will create maximum profit? And in finding this optimal quantity, we're going to need to apply the first derivative test and the second derivative test that we have discussed in the previous slide. Let's apply the test to profit maximization. This is profit equals revenue minus cost. The necessary condition or the first derivative test is the first derivative of profit with respect to Q should be equal to 0. So, because profit is revenue minus cost, the first derivative is the first derivative of profit with respect to Q is equal to the derivative of revenue with respect to Q minus the derivative of cost with respect to Q. It should be equal to 0. And then when this derivative of cost with respect to Q is moved to the right of the equation, we have here the derivative of revenue with respect to cost should be equal to the derivative of cost with respect to Q. Because in economics, the derivative of revenue with respect to quantity is called marginal revenue, and the derivative of cost with respect to quantity is called marginal cost. So the necessary condition or the first derivative test is the marginal revenue should be equal to marginal cost. So to find maximum profit, the quantity, the optimal quantity should satisfy that the marginal revenue is equal to marginal cost. That's the necessary condition. And the sufficient condition to find the maximum profit, the second derivative of profit with respect to Q should be less than 0. So when it is applied to this profit function, the second derivative of profit with respect to Q is equal to the second derivative of revenue with respect to Q minus the second derivative of cost with respect to Q. It should be less than 0. When the second derivative of cost with respect to Q is moved to the right, we have here the second derivative of revenue with respect to Q should be less than the second derivative of cost with respect to Q. Or we can also say that the condition to make sure that we have a maximum point in this profit maximization is that the derivative of marginal revenue should be less than the derivative of marginal cost, or the slope of marginal revenue should be less than the slope of marginal cost. This is the graphical illustration of the first derivative test, or the necessary condition. We have a typical cost curve here, and this is the revenue curve. Because profit is revenue minus cost, so when the revenue is greater than the cost, we have positive profit. And then when the revenue is less than the cost, we have negative profit or loss at this point, for example. And then at this point, the revenue is equal to cost, so we have a zero profit, or it is a break-even point. And it is also a break-even point because cost is equal to revenue. And when the profit is at maximum, here the slope is 0. When the profit is at minimum, the slope is also 0. We can also see here that when the slope of the profit is 0, the steepness of the revenue is just equal the steepness of the cost. So the slope of the revenue is equal to the slope of the cost. The slope of the cost is equal to the slope of the revenue. Or we can also say, because the slope of revenue is marginal revenue and the slope of cost is marginal cost, so at maximum and also at minimum, the marginal revenue is equal to marginal cost. The marginal cost is equal to the marginal revenue. That's the necessary condition. In this necessary condition, we have two possible results, maximum or minimum. And then this diagram can better illustrate the second derivative test. This is the profit graph, the profit curve. And then this is the first derivative. We can see here that when the profit is at maximum and when the profit is at minimum, the first derivative is equal to 0. The first derivative is equal to 0. So from this necessary condition, from this first derivative test, we cannot decide whether it is maximum or minimum. Only from the second derivative test, only from the sufficient condition, we can decide whether it is maximum or minimum. When the second derivative is less than 0, we are sure that it is a maximum. And when the second derivative is greater than 0, it is a minimum. So it is maximum loss, not the maximum profit. This is the maximum profit when the second derivative is less than 0 and the first derivative is equal to 0. This is another graphical illustration for the tests. This is the profit curve, and then this is the marginal cost and marginal revenue. At minimum point here, at minimum point of the profit, the marginal cost is equal to marginal revenue. The same thing as the maximum point here, marginal cost equals the marginal revenue. That's the necessary condition. At this necessary condition, marginal cost equals the marginal revenue. At minimum, the marginal cost equals the marginal revenue. And then to make sure that it is a maximum, we need to apply the sufficient condition. The sufficient condition says that the slope of marginal cost should be greater than the slope of marginal revenue. And it is found here that at this point, the slope of marginal cost, the slope here, we have a positive value of the positive value of the slope of marginal cost. Here, for example, the slope can be 2, and we have a negative value of the slope of marginal revenue. For example, the slope of marginal revenue is -1, because 2 is greater than -1, so it means that the slope of marginal cost is greater than the slope of marginal revenue. And for this minimum profit, at the minimum point of the profit here, the slope of marginal cost is less than the slope of marginal revenue, because the marginal cost here is steeper. So for example, the slope of marginal cost can be, for example, -2, and the slope of marginal revenue, for example, can be -1, because -2 is less than -1, so the slope of marginal cost is less than the slope of marginal revenue. So this is not the maximum point, this is the minimum point. And the maximum point is here, when the slope of marginal cost is greater than the slope of marginal revenue. Right, that concludes our discussion on the concept of profit maximization using derivatives. And an example on specific cost and revenue functions, cost and revenue equations, will be found in the part 2 of this optimization videos. Thank you. I hope this can help you understand the concept of applying derivative in doing optimization. Thank you.